Okay, this is for Sacramento City College. It's August 30th, 2020, about 3:25 p.m. on a Sunday. Okay, this is the modules in Canvas. Just want to point a couple things out. So I uploaded the lab. So this is where you download it from, and then this is where you turn it in at. So everything else is already the way it was. Oh, and then I uploaded the PowerPoint that we're going to watch right now. So you would download that from here. Okay, so this lab right here looks like this. Okay, you read through it. You got a couple of questions to answer, not a whole lot. And this will count as our lab number 1. And it is due a week from tomorrow, or as you're reading this, if you're reading this on Monday, a week from today. Okay, and then the PowerPoint is what we're going to look at right now. That's this guy right here. And I scheduled a Zoom meeting for tomorrow at 6, or actually Monday, perhaps today as you're reading this. So upcoming events, Monday, August 31st, 6 p.m. Okay, that's for us right here. Okay, so let's head over to the PowerPoint. Alright, so I was going through chapter 1 of your book, and then there are some important things that are mentioned in there that we really should point out. And it talks about science, what science is, and maybe some of your other science courses also go through this stuff as well. But science consists of all theories and laws that are general truths of nature, as well as the body of knowledge they encompass. I took these directly from Urone. I was reading through them. I said, that's kind of important to go through. Okay, scientists are continuously trying to expand this body of knowledge and to perfect the expression of the laws that describe it. Physics is concerned with describing the interactions of energy, matter, space, and time, and it is especially interested in what fundamental mechanisms underlie every phenomenon. Okay, so energy is like the most important, really. Energy is like the single most important thing you could ever study anywhere. I got a picture of Galileo up here, 1564 to 1642, called the father of modern science. Alright, so physics aims to describe the function of everything around us, from the movement of tiny charged particles to the motion of peoples, cars, and spaceships. I mean, the motion of galaxies, or what the universe is doing. Just everything from the smallest to the biggest. In fact, most everything around you can be described quite accurately by the laws of physics. The laws that we encounter, Newton's laws and that good stuff, that's all stuff that in your everyday life you can figure out what's going on around you. Where it starts to break down is when we start getting close to the sizes of atoms. Then quantum mechanics takes over for classical physics. And if we're traveling near the speed of light, then general relativity takes over for classical physics. But you're not going to be dealing too much with things the size of an atom, or you're not going to be traveling near the speed of light. Newton's laws of motion and all these other laws we're going to be covering are perfectly fine. Physics describes how electricity interacts with the various circuits inside your smartphone. This knowledge helps engineers select the appropriate materials and circuit layout when building the smartphone. Next, consider a GPS system. Physics describes the relationship between the speed of an object and the distance over which it travels, and the time it takes to travel that distance. When you use a GPS device in a vehicle, it utilizes these physics equations to determine the travel time from one location to another. Now you got Newton up here. Notice that Galileo died in 1642 and Newton was born in 1642, kind of like passing the baton. Newton was born in December, and Galileo, I believe, died in January. So it wasn't like Newton was in his mom's womb. He wasn't conceived yet when Galileo died, but still, it's kind of like passing of the baton. Okay. The laws of nature are concise descriptions of the universe around us. They are human statements of the underlying laws or rules that all natural processes follow. Their discovery is very important, is a very human endeavor, with all the elements of mystery, imagination, struggle, triumph, and disappointment inherent in any creative effort. The cornerstone of discovering natural laws is observation. Science must describe the universe as it is, not as we may imagine it to be. Okay, so now the book starts talking about models. So we talk about the scientific method. So you make an observation. That's kind of like what's right here. Observation. You see something. You ask a question. Okay. Hypothesis really isn't that necessary. Hypothesis kind of implies you're jumping to conclusions. Like when detectives are looking into a murder case, they say they focused on a suspect way too soon and missed the real guilty party because they got so focused on one, jump to conclusions. I can't remember what the word is, but there's something that defense attorneys use all the time to say they kind of use this part here where they came up with a hypothesis that says, oh, that Joe guy over there, he's guilty. And then they try to make the evidence fit that guy's guilty when the evidence was kind of showing, wait a second, maybe this guy isn't guilty. Maybe you need to skip this step and just use what the data tells you. Okay, use what the clues tell you. What does the evidence tell you? And so I never really liked that hypothesis thing. I like the question, ask the question, do an experiment to try to answer the question, and then see where the data leads you, see where the evidence leads you. You analyze the data, and from that you come to a conclusion. So I don't know this hypothesis thing, I never liked that. You want to just keep an open mind, don't try to guess what's going to happen, and just let the data take you to the right place. I mean, the hypothesis the Greeks had was that heavier masses would fall to the ground faster than smaller masses. They never did the experiment. They just stopped at the hypothesis. And so, do the experiment Galileo did, and he said, whoops, the Greeks' hypothesis was wrong. It was wrong. Okay, as scientists inquire and gather information about the world, they follow a process called the scientific method. This process typically begins with an observation and question that the scientist will research. Next, the scientist typically performs some research about the topic and then devises a hypothesis. Typically, I don't know, not that it's typically, maybe sometimes. Then the scientist will test the hypothesis by performing an experiment. Finally, the scientist analyzes results of the experiment and draws a conclusion. Okay, so physical quantities. We define a physical quantity either by specifying how it is measured or by stating how it is calculated from other measurements. Measurements of physical quantities are expressed in terms of units, which are standardized units. There are two major systems of units used in the world. The SI system, international system, of course it's French, so they have the words the other way around. They call it Système International or something like that. Anybody know French out there? The units. So instead of international system of units, they would have Système International de units or something like that, also known as the metric system. Most people call it the metric system. Now your book refers to English units, but most people call that the British system or imperial system. I hear British system all the time. I haven't really heard these other things. Okay, English units were historically used in nations once ruled by the British Empire. Kind of like once upon a time, before we were the United States, we were ruled by the British Empire. Canada, Australia, many other countries. Now, who still uses the British system? Okay, we're not there yet. So physical quantities and units. Here we go. Currently, only 3 nations in the world still use the British system as their primary system for units. One is Liberia on the western coast of Africa, and this would be Liberia right here, western coast of Africa. They still use British units. And then there's Myanmar, also once known as Burma, in Southeast Asia. There's that country there. What is the other country that would still be using the British system? We can figure this out. Okay, in all your travels around the globe, have you ever been to a country that has distance signs in miles instead of kilometers? In other words, do you ever remember being in a country, like if you went to Liberia, you drove around and say the next town is 10 miles away, not that it's 14 or 16 kilometers away. Same here, it would say miles. So is there another country that just uses miles for distances, and that country is, oh no, it's us, the US, we're the other one. That's the only other reason the other two can stick to the British system, because the United States economy is so huge. You know, you go buy a Mercedes or a BMW made in Germany, and you buy them, and they've got the speedometer in miles per hour, not kilometers per hour. Why? Because they made it specially for the U.S. market. So our economy is so huge, other countries enable us to continue to keep with the British system. Okay, we still measure distances in inches, feet, yards, and miles. We still measure weight in pounds instead of newtons. In the SI system, the unit of mass is the gram, very well known and used. Talk about kilograms, all that kind of stuff all the time. In the British system, the unit for mass is a slug. Is the slug, in the slug, is the slug. It should be is the slug. Anyway, I'm not going to bother changing. Have you ever heard of anyone saying something has a mass of 32 slugs or anything like that? I've only seen the word slug twice. Both times in lower division physics books talking about the unit systems. They would list the British system versus the SI system, and then they have mass and grams for the SI system. They got to list what it is for the British system. They have the word slug there. Those are the only two times I've seen that word used as a unit for mass. So we don't use mass much. We talk about pounds, but pounds are the same as newtons in the British in the SI system. All right, and then you got the length is meters, mass is kilograms, time is seconds. Now they've got ampere. Ampere is coulombs per second. So you got seconds over here. So I don't know why we don't have charge and coulombs. Seems like charge and coulombs would be better than ampere, but they've got ampere there instead as the basic fundamental units. Yeah, ampere is actually coulombs per second. Second is one of the other fundamental units. So why is it coulomb? Why don't they say coulombs the one over here? I don't know. Hey, oh, this is the end? Oh, this is the end. Okay, so let's try some of our problems. Okay, so this is online number 1. This is the one that's due Wednesday, September 9th. I'll have another one up this week. That'll be due a week later. You got your quiz September 9th as well. Okay, in Urone, soccer fields vary in size. A large soccer field is 115 meters long and 85 meters wide. What is its dimensions in feet and inches? Okay, well, let me point something out here. So you've got this to download. This is our lab number 1. If you go back up here a ways, there it is. I just went right by it. There you got length. You got what centimeters and inches are. You got feet and meters. You got miles and kilometers. Okay, so you've got all of these guys here. Okay, so, and this is not exact because we probably need more digits out here, 1.6 something 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 to make it exact. Okay, so, and then the feet to miles thing is weird, and it's just, so anyway, there's your conversions right there for length. So, now we have how many feet there are per meter. That was back over there someplace, I think. So you have 115 feet, or meters. And you want to get rid of the meters and get feet, you simply take this conversion ratio. You want to make sure, if you're trying to get rid of meters, make sure meters goes on the bottom. So the meters will cancel out. And you get 377.3 feet, or 377 feet long. Your textbook loves 3 digits of accuracy, okay? 3 digits. So you can see that we had 3 digits there, we have 4 digits there. So, but because we only have 3 digits with this number, they rounded it down to 3 digits. Now when we go back to do the next one, we used 4 digits because that's what we got over here. So I guess they've shown that it's best to keep every single number you have until the very end. When you get to your answer, then round that down to the least number of significant digits that you have. So you have 2 numbers that have 9 significant digits, 1 number that has 2 significant digits. You keep the 9, you keep the 9, you keep, and then the 2. And then when you get the answer, you got to round it down to 2 because only one of your numbers had 2 significant digits. All right, 85 meters, 1 foot. Again, there's the same thing. We get this, and then so then 85 only has 2 significant digits. That's why they rounded it to 2.8, 2 significant digits. And then we got the feet, 12 inches per 1 foot, just like up here. Do the same thing. Round it down to 3.3 times 10 to the third inches because we started with 85 meters. Mount Everest at 29,028 feet is the tallest mountain on Earth. What is its height in kilometers? Well, we simply go 29,028 feet, do the conversion between feet and kilometers. You get 3,281 feet in 1 kilometer. You get 8.847 kilometers. So they're keeping the 3 digits there because we have, 4 digits there because they have 4 digits and 4 digits. Tectonic plates are large segments of the Earth's crust that move slowly. Suppose that one such plate has an average speed of 4 centimeters per year what distance does it move in 1 second at this speed? What is it? Is its speed in kilometers per million years? So it moves 4 centimeters per year. Okay. What distance does it move in 1 second? So what we want to do is get rid of the. So we get rid of the meters here. Okay. We turn into 1 year. So you got the 1 year equals 365.25 days. That's because of leap year. So we can use 365. It's not going to make a big difference in the long run when we talk about this much time. So then 1 day, 24 hours, 1 hour, 3,600 seconds, 60 seconds, or 60 seconds in 1 minute, 60 minutes in 1 hour. 60 times 60 would be 3,600 seconds in 1 hour. So it moves in 1 second 1.3 times 10 to the minus 9 meters, or 1.3 nanometers. That's like the size of a nucleus, okay? But that's in a second. That's in a single second. And the seconds will add up over time, over a long period of time. Okay, what is its speed in kilometers per million years? Okay, so how many kilometers will it move in a million years? So you got your 4 centimeters per year. You got your 1 meter per, just all your conversions. So you end up with 40 kilometers in a million years. So it'll move like between, I don't know, Sacramento and Placerville in a million years, that distance there. Okay. We don't have to refer to table 3.1. To determine the average distance between the Earth and the Sun, then calculate the average speed of the Earth in its orbit in kilometers per hour. What is this? Okay, so velocity is distance over time. We're talking about the orbit of the Earth around the Sun, so it's the circumference of a circle. Okay, so the radius we would have looked up in table 1.3 would have been 10 to the third kilometers. Okay, so the radius would be not 10 to the third. It's more like 10 to the 8th. 10 to the 8th kilometers. I knew that was wrong when I said it. 10 to the 8th kilometers. 10 to the third would be 1 kilometer. 10 to the 8th kilometers. Okay, so then we got, this is the distance in kilometers that it travels when it goes around the sun once, completes a 360-degree orbit. It does it in 365 days. Okay, 365.25 days. Okay, so we want to do is get it in kilometers per second. So here we're converting the days into hours. Now we're converting the hours into seconds. So we're actually moving 20 kilometers per second. 20 kilometers might be about the distance between Sacramento and Davis, maybe. So that's how fast we move in 1 second. We don't feel it because we're moving with the Earth, but the Earth is whipping around the sun pretty fast. It completes completes a complete orbit around the sun in a single year. So then what is this in meters per second? Well, we got 20 kilometers per second. You know, you want to get to meters. You want to do the conversion. There's 1,000 meters, 1 kilometer. Put the kilometer on the bottom so the kilometer will cancel out. 2.0 times 10 to the 4th meters per second. Okay, so that's pretty fast. So this is where we got into that percent uncertainty stuff, so you just kind of maybe need to be aware. I'm sure if you're going into stuff like medicine, nursing, or anything like that, you're going to have to learn these in some other class and more in depth. If you're going into maybe anything you go into, you'd have to know this. I'm not sure. An infant's pulse rate is measured to be 130 plus or minus 5 beats per minute. What is the percent uncertainty in this measurement? Well, it's the uncertainty divided by the measurement, times 100. So the uncertainty is 5. So it could be anywhere from 125 to 135, which means that each time you take the baby's pulse, you're 67% confident you'll fall within the range of 125 to 135. You're in that range. I think it's supposed to be 66, 67%. You'll be within that range. So you just take that, multiply it by 100, you get 3.84. But the uncertainty was only one significant digit, so they rounded it to 4% efficient. Okay, then what is the area of a circle? 3.105. This is actually 22 in Urone. And that's all there is to it. Kind of weird. So now here's the thing you got to remember. This is diameter. Okay, this is diameter. So you got to divide the diameter by 2. Because that's pi r squared. That's radius. Okay, so you get pi d squared, d over 2 squared. You multiply it out, 7.557 centimeters squared. And then this is chapter 2. We're not there yet. All right, so I think that's everything for this. And I'll have a Zoom session tomorrow if you get to watch this. I'm going to upload it now. I don't know how long it'll take. If I was at Sac State, it would take like 20 minutes. My home computer can take anywhere from 6 to 12 hours. So it's like 3:46 right now, so we'll see. All right, so I'll start sending this out now. So let me say good night for now. I think I covered everything. Good night. I'll talk to you tomorrow.